Okay, gang, welcome back to GO2. This recorded lecture is going to cover PowerPoint number 5. That's on oceanic circulation. The last recorded lecture covered PowerPoint number 4. That was on atmospheric circulation. And as we'll find out through today's lecture, atmospheric and oceanic circulation are intimately linked to one another, at least circulation in the surface ocean. And so in the last lecture, we talked about atmospheric circulation. We finished that up on Monday of last week, and then we started on oceanic circulation on Wednesday. We're finishing up oceanic circulation on Monday, the 7th of February, and then we'll move on with PowerPoint number 6, which is on plate tectonics, beginning on Wednesday. And so this slide that's showing here is kind of the synopsis of atmospheric circulation that we established last time, and we established it sort of piecewise, and we started with this idea that the solar radiation flux is not distributed equally on the planet. There's a higher flux of radiation from the sun at the equator or at low latitudes than there is at higher latitudes because it's distributed over a larger area, right? And so we have this net radiation flux in the solid line here that's very high at the equator and very low at the poles, and that's really the energy that we're receiving. Then the Earth processes that energy and it does all kinds of things with it at the surface, but inevitably it gets re-emitted as infrared radiation back out to the solar system or to outer space. And this dotted line is the outgoing infrared radiation. Okay, and so you have on if we're looking at the Earth here, you have a lot of solar radiation coming in here and not as much coming in here at higher latitudes, right? And it gets progressively greater as we move towards the equator in both directions. And because of that, you end up with an infrared flux going out, right? Going back out, that kind of looks like this, right? It's higher temperature at lower latitudes, and as a result, the air at lower latitudes gets heated preferentially. And so what we said is that there are two fundamental properties of air that you really need to understand, and that's that warmer air is less dense than colder air. It is lower pressure, right? Is kind of a way to think about that. It creates lower pressure systems. Warmer air is lower density, tends to rise. And warmer air can also hold more moisture, right? And so if we're preferentially heating the air, if we're preferentially heating the air here in this region, right, it's going to create a lower pressure system, and air is going to flow in from the sides where it's colder and higher pressure, right? And so we established this flow in the atmosphere where you have warmer air flowing from 30 degrees. What am I doing here? There we go. We have air flowing from 30 degrees towards the equator in both directions. It gets warmer as it approaches the equator and it begins to rise. That's called the intertropical convergence zone. But as it begins to rise, it starts to cool off, right? Because the upper atmosphere is colder than the ground and the surface. And so as it cools off, it begins to move laterally. As it moves laterally, it continues to cool until it begins to sink at about 30 degrees north and south, right? As it sinks, it starts to warm back up, right? And so it comes back in, starts to warm back up. It actually moves in both directions there. It's a divergent zone. And so you have this cycle where warm air comes from 30 degrees, and it moves towards the equator. It continues to warm up as it moves towards the equator. It begins to rise because it becomes so low density, it becomes so warm that it starts to rise. But as it rises away from the Earth's surface, it starts to cool off. And as it cools off, eventually it achieves neutral buoyancy and it begins to move laterally in both directions. But more importantly, or also importantly, it starts to drop its moisture because it cools down and it can't hold as much moisture. And so if we kind of extend that back to this, we have these circulating cells here that warm air rises at the ITCZ, clouds form, precipitation occurs, it moves off laterally in both directions, it begins to sink back down towards the Earth. It's cold, dry air in the upper atmosphere at this point, at this point here, it's cold and dry. And so as it returns to the Earth, it warms up and it can hold more moisture as a result. And so if we look at the distribution of forests and deserts on the Earth's surface, what you see is that they're primarily concentrated, the forests are primarily concentrated around around the equator rather, and deserts are primarily concentrated around 30 degrees north and south latitude. Okay, and that's a direct result of this Hadley circulation that you see here. Warm air rising to the equator, precipitation occurring, the colder air, or the air as it cools, moving off to the sides, sinking back down at 30 degrees north and south latitude. Okay. Now, the reason that it forms these three circulation cells, as we established last time, is because of the Coriolis effect. Without the Coriolis effect, it would look something more like this, where there would just be a single convection cell in the north and a single convection cell in the south. But because we have the Coriolis effect, that breaks down into these. And it breaks down essentially because as air is flowing across the surface in the northern hemisphere, it tends to deflect to the right off of its path. And so if we think about just one continuous flow coming towards the equator, it would continually bend to the right off of its path, and it breaks down. And so that establishes this three circulation cell system in each hemisphere. If we were spinning faster, there would be more cells. If we were spinning slower, there would be less cells. If you look at some of the gas giants, if you look at like Jupiter, for example, it's spinning very fast, and there are narrow bands, lots and lots of narrow bands in its atmosphere. Okay, and the Coriolis effect is effectively, it's essentially just this. Let's see if we can grab a new page here. So essentially, it's just the fact that we live on a sphere that's spinning. And so if you're at a different position on this sphere, you travel a different amount of time, a different distance per unit time. So for each hour, for example, if this little slice here is 1 hour, if you're at the equator, you travel a great distance, whereas if you're standing near the pole, you don't travel very far at all, right? And so if you have 2 points here, we'll just call them A and B, and point A is traveling this direction at some speed. Point B is traveling the same direction at a lower speed, right? And you send some projectile from point A up towards point B. It's not going to go directly towards point B because here at point A, you're traveling to the right. And so it's actually going to travel in some line like this, right? Now, if you're standing at point B, you're traveling to the right as well, but in the same amount of time that point A travels all the way to here, you only travel to this point here. And so this projectile actually misses you to the right. That's an example of in the northern hemisphere. And so if you project that onto this globe over here, you see if you're standing at point B here watching the projectile come towards you from A, initially it appears that it's coming straight towards you, but as time progresses, it appears that it's bent to the right. In reality, it's following a straight path from point A here to point X, but it appears to an observer on the Earth's surface here, that it's bending off of its expected path to the right. And so that's the Coriolis effect. And it affects atmospheric circulation. It affects many things. We'll find out that it affects oceanic circulation as well. But this is kind of a graphical representation of the velocity that you're traveling based on your latitude. And so out here at the equator, you're going about 1,000 miles an hour, but at the pole, you're not traveling at all. You're just spinning in place, rotating. Okay, and so when you apply that Coriolis effect to these surface flows, right? And so it's important, what we're talking about here is just, let's see if I can get rid of this. Let's go with this one. So we have the Earth, right? Go. That's the Earth, and so it has. We have 30 north and 30 south. Might help to draw it like this. So these are the Hadley cells here, right? They come in this way. The intertropical convergence zone comes out. Right. That's the atmosphere circulating, right? Now, the surface winds that we're talking about are these, right? So it's moving that direction there, that direction there. And from here to, from 30 degrees to 60 degrees, it's moving that direction, right? And similarly here, it's going to be going that direction, right? This is the equator. This is 30 north, 30 south, 60, right? Okay, and so the surface winds are going this direction all around the Earth, right? Like the diagram is showing. But what we're saying is that because of the Coriolis effect, they're bent to the right in the northern hemisphere and to the left in the southern hemisphere, right? It's bending off of the path, right? And so if you're walking down this arrow up here, you're bending off to the right, going that direction. And similarly, these flows that you would expect to be going this direction are actually bending to the right. Okay, and so that sort of turns this diagram here into this one, right? And so we have these dominant wind patterns, really two of them. They're these polar easterlies on both the poles, but they're restricted to the poles really. The major wind patterns across the surface are going to be these trade winds coming from the northeast to the southwest and the southeast to the northwest, and the westerlies blowing from west to east. And the trade winds are just north and south of the equator on either side, and the westerlies are around 45 to 50 degrees north and south, so just below the 60-degree line. Okay, and so that really gets us to this picture here, which is this synopsis of atmospheric circulation. You have the Hadley cells circulating, warm air flowing toward the equator from 30 degrees north and south, converging, warming and rising, and then moving away in both directions and cooling as it does. And as it cools, moving vertically and then laterally, it drops all of its moisture. And so by the time it gets to 30 degrees north or south, it's quite dry. And it sinks back towards the Earth, warms up, and starts to drive evaporation, right? Warmer air can hold more moisture. It's also less dense. Those are the two critical things you need to know about this. All right. And if you know those two things, it basically gets you all the way to this circulation pattern, which tells you a lot. Okay. So now how does that relate to ocean circulation? Well, it relates sort of directly in a number of ways. Let's get the other PowerPoint up here. Okay, so this is PowerPoint number 5, which is ocean circulation. And so this figure on the left here on the first slide is basically exactly what you were seeing in that last slide, summarizing atmospheric circulation. You have the trade winds blowing on the north and south side of the equator, and the westerlies blowing up here in between 30 and 60 degrees. It's the colors are obviously showing it's warmer at the equator in the tropics than at the poles. Okay, so water is a critical component of all things on Earth because it cycles continuously. Really, that's what this is saying here. It carries a lot of things with it, nutrients, energy, gases, other matter, which are all really important. And the cycle, the system as a whole is composed of all of these individual components, and we're trying to walk through each one. And so we've really established how the atmosphere circulates because of the energy balance. And as you can imagine, when wind blows, it creates a friction, a traction on water, and that sets water into motion. And we'll talk about exactly how that happens. But in general, water moves around a lot on our planet. This idea of the hydrological cycle is central to a lot of things in earth sciences. And it's as many things are, and another example of a steady state. And so you can see we have some unit here. It's 10 to the third cubic kilometers a year, so 1,000 cubic kilometers a year. About 361 evaporate out of the ocean. Some amount of that just rains right back down into the ocean, so 324. Some amount of it, though, is carried, just transported through advection. That's just a word meaning transport, physical transport, over land where it rains or snows. Some of that snow can get trapped on land, and that would drive the system out of steady state. But as long as it's in steady state, which it is here, you have some amount of overland flow that's going to return water through streams and rivers back to the ocean. And so there's precipitation coming directly into the ocean, 324 and 37 flowing through streams and groundwater back into the ocean. 324 plus 37 is 361. So we're at steady state. That means the volume of the ocean is not going to change in this scenario, right? Obviously today, the volume of the ocean is increasing. Sea level is rising because we're melting glaciers on land, which is contributing additional water to the ocean, right? But in general, this is what's occurring. Now, the amount of evaporation and resultant precipitation that occurs is directly related to the amount of energy in the system. And so if we're increasing the amount of energy at the surface of the Earth, we can expect more evaporation and more precipitation, right? In general, storms will increase in frequency and intensity, okay? So if we talk about where the water on the planet is, the vast majority of it is in the oceans. About 96.5% of all of the water is in the oceans, right? That's obviously salt water, and so there's no percent freshwater there. But if we look at freshwater specifically, it's broken up about 2/3 in ice caps and glaciers, and about one-third in groundwater. Okay, fresh groundwater. Lakes and rivers account for a very small amount of the actual fresh water on the planet. Most of it is in groundwater or locked up in ice, and so that's why we, frequently we're drilling water wells to access groundwater. Okay, a very, very small fraction of it is in the atmosphere, right? Okay, so water in the atmosphere is not distributed equally around the planet. Obviously, we established that last time. Warm air can hold much more moisture than colder air. And air cools as it rises above Earth's surface, rises in altitude. And so that concept really gave rise to that intertropical convergence zone. But this PowerPoint is really about the circulation of the oceans. So how does water move when it's in the oceans? And there are really two ways that it moves. One is through wind-driven circulation, and that, as you can imagine, is restricted to the uppermost portion of the ocean. And the other way is through density-driven circulation. And just like density drives circulation in the atmosphere, it drives convection in the ocean. And it does so through really two factors: temperature, just like we had with air, but when you're dealing with water, with fluid, the salinity has a lot to do with the density of a solution. And so if we can, since the ocean is salty, if it could get progressively saltier in certain spaces or certain places, that water would increase in density and tend to sink. Okay, and so we'll find out how that happens later in this lecture. All right, and so that really all relates to this greater question of how is energy transported in the oceans, because that's really what we're trying to understand, is how the energy imbalance that we get on the planet as a result of living on a sphere is processed by the climate, or is processed by the Earth, which sort of generates climate. And I think you're probably getting that idea at this point, that climate is largely driven through the energy imbalance, right? Okay, and so the first component of oceanic circulation is going to be wind-driven transport, Okay, and so it's just surface ocean currents. Like I said before, if you have a glass of water and you blow across the surface, it starts to ripple, and that's water moving. But no matter how hard I blow, I'm probably not going to stir up the bottom of, say, like a pint glass. I probably can't blow that hard. And even if I could find a deeper glass such that no matter how hard I blow at the surface, I'll never stir up the bottom of that glass, right? That's because there's a sort of dissipation of energy when that energy is imparted on the surface of the water. You can kind of think about it as layers. You know, I blow on the surface of the water and it goes into motion, and then the motion in that layer sets the layer below into motion, and it progressively moves downward through the water column, sort of propagates downward. But there's a decay in energy, right? If I blow on the surface of the water, the whole glass doesn't mix evenly. The surface moves fast, the bottom doesn't move at all. And so it's this sort of linear decay between the two. The motion gets progressively less and less as you move downward. Okay, now I wish that were the full story. Unfortunately, it's not, because we have the Coriolis effect on the planet, right? And so if we're saying that all objects are deflected to the right in the northern hemisphere and to the left in the southern hemisphere, well, that applies to water as well as air. And so as water is transported across the surface in the northern hemisphere, its path tends to bend to the right. Okay, now that has a slightly more complex implication for water than it does for air, because the water sets the water below it into motion. And if you think about it as that layered concept, what ends up happening is this. It's a very famous concept in physical oceanography called the Ekman Spiral. And what it is this. When wind blows across the surface of water, okay, it sets the surface into motion. Because the Coriolis effect, that motion is generally not parallel to the wind. It's actually deflected off. This would be an example for the northern hemisphere, about 20 to 45 degrees to the right, depending upon the kind of currents. When that water gets set into motion, it sets the layer beneath it into motion, but that too is deflected to the right, okay? And it propagates downward, continuing to deflect to the right as you propagate downward through the water column. This concept is called the Ekman Spiral, and it creates a sort of more general concept known as Ekman transport. And what Ekman transport says is that, well, if the wind blows in one direction, it sets the water into motion, but that water is deflected by the Coriolis effect as it propagates downward. And as a result, if you add all of these arrows together, you'll end up with the net flow for water. And that flow is 90 degrees to the right in the northern hemisphere and to the left in the southern hemisphere of the dominant wind direction. Okay, so the wind blows one direction, and water generally is transported 90 degrees from that. Okay, there's a dog barking outside my apartment. Okay, so Ekman transport. The wind blows and the water moves at 90 degrees, generally speaking. Okay, now this has broad implications, right? If we go back to the trade winds blowing across north of the equator and south of the equator, well, they're gonna exert traction or friction on that water in the ocean there in the North and South Pacific, and they're gonna set the water in motion. It's gonna generally go from east to west in there, but it's also gonna get pushed off of its course, sort of towards the center of the ocean basin. Okay, and so if we think about that in terms of one single ocean basin, maybe North America is over here and Asia is over here, it's the North Pacific. The trade winds are blowing from east to west across just north of the equator, and the westerlies are blowing from west to east up near 45, 50 degrees north, so just around the Canadian border. And so that pushes the water, but Ekman transport continually drives that water towards the center of this circle, this circulation pattern. We use the word gyre to refer to that, G-Y-R-E, it's right there, gyre. A gyre is just this big circulating water mass in the ocean. And it results because of the trade winds and the westerlies and Ekman transport. And there's a big gyre in each of the ocean basins, as we'll see in a moment. But generally speaking, as water is transported by the trade winds and the westerlies, it's actually driven towards the center of the gyre, which creates kind of an interesting effect. It actually creates a little hill of water. You can measure it using satellites, for instance. There's a few meters of difference between the center of the ocean and the edges because of that Ekman transport continually driving water to the center. It drives other things too. You may have heard of a giant raft of trash sitting out in the middle of the Pacific. That's because of this type of convergence there. When you pile that water up, though, it kind of gets thick, and it tends to do two things because it's a fluid. It forces itself downward, and it also forces itself back downhill towards the outside. If you thin that surface layer, the opposite would happen. You'd have upwelling. Okay, and that happens at the equator, as we'll see a little later. So you have this thickening of the surface layer, which causes this flow back downhill. Now, as those currents go back downhill, these geostrophic currents, that's coming from the center of the gyre back towards the outside, right, in every direction. And when you do that, what ends up happening is that because of the Coriolis effect, it bends to the right. We're in the northern hemisphere, it's bending to the right. And so it's driving this clockwise circulation pattern, really. It's really these return flows being bent to the right that really keep this gyre circulating. Now, there are a couple of other things, obviously, that keep the gyre circulating. If we look at the distribution of continents, right? Obviously, if a current is flowing across the North Atlantic with the trade winds, it's going to run into North America. And being in the northern hemisphere, it's going to tend to bend to the right, and so it just continues around. And the westerlies pick it up, they push it off to the east, from the west to the east, and it hits Europe and Africa, and it bends back down around to the right, returning to the equatorial current. Okay, and if you look at any ocean basin, they have this pattern. In the southern hemisphere, they rotate counterclockwise because of the Coriolis effect. Northern hemisphere, they rotate clockwise because of the Coriolis effect. Okay, and so the green arrows on this figure are showing the trade winds, right, and the red areas are showing the westerlies. It's kind of hard to see, but there are dotted lines and solid lines. The dotted lines are showing warm currents. Oops. The dotted lines are showing warm currents, and the solid lines are showing cold currents. And as you can imagine, the currents coming up the western boundaries of these basins, we call them the western boundary currents, they're generally warm water currents. And so the Gulf Stream is a famous example of that. It flows from the Caribbean up through the Gulf of Mexico, through the Straits of Florida, and then up off towards the UK, carrying warm water. If you guys have ever been to Florida or the Carolinas, you know the water there is really warm because of the Gulf Stream. Here in California, it's really cold. Hopefully everybody's been to the ocean here. It's really cold here in California because we have this cold water current, the California current, coming down from Alaska down sort of the coast of British Columbia, and it kind of breaks off the coast near sort of like Pismo Beach, Ventura area. I think it kind of breaks off the coast, but in general, the water's really cold here because it's coming from the north. There's also a lot of upwelling here, bringing cold, deep water up to the surface, which we'll talk about momentarily. But in general, each one of these ocean basins is going to be characterized by warm water currents flowing up the west side of the basin to higher latitude, taking the equatorial current up to higher latitude, and there's going to be a return flow down the eastern boundary of the basin, bringing cold, high latitude water back to the equator to be warmed back up. Okay, and that's true of every basin. All right. Another consequence of Ekman transport is that when you have what are called longshore winds, they're quite common, especially on the western boundaries of continents, it turns out. You get wind blowing down the coast. This would be in the northern hemisphere here. If you have wind blowing straight down the coast, it's going to push the surface water at 90 degrees to the right, away from the coast. This occurs down the coast of California quite a bit. Maybe this is Big Sur. We have mountains right next to the coast, and you get strong winds blowing down the coast. It pushes the surface water away from the coast, allowing deep water to come up and fill in for it. Now, deep water is cold, as you can imagine, but it's also full of nutrients for reasons that we'll talk about later, which is really important. It supports lots of photosynthetic production, which supports higher trophic levels like fish, which are really important for people, for food source and the global economy. Okay. Another interesting implication of of these currents is that we have unexpectedly warm or cold temperatures at different latitudes. And so this is an island in the North Atlantic. Let's see if we can go. It's somewhere up in here off the coast of the UK. And as you can see, the Gulf Stream comes right up the coast of the eastern US, eastern North America, and then it shuttles off towards the UK. And if any of you guys have ever been to the UK, it's pretty warm there. It's at the same latitude as parts of like Labrador, Canada, or Newfoundland, which is really cold. The UK is pretty warm comparatively. It rains a lot there, more than it normally would at that latitude. And that's all just because the Gulf Stream is taking warm water up through the North Atlantic and just kind of blanketing the UK in warm water continuously. And that has profound effects on the climate in the region, as you can imagine. Okay, so that sort of describes wind-driven circulation. Now, as we said, with this whole Ekman Spiral business, wind-driven circulation only propagates so deep, and that depth is maybe 100 meters, maybe 200 meters maximum, two football fields, something like that. It's not very deep. Deep water, the ocean out off on the abyssal plain. So if you get off the continental shelves, the ocean is around 4,000 to 5,000 meters deep on average, and so the upper ocean, wind-driven circulation, only propagates a couple hundred meters deep. Well, that leaves a massive reservoir down there that doesn't mix on that same time scale, but really via the same process. And that's really important. And so if we go back up here, this slide, how does water in the oceans move? Wind. Well, the surface ocean moves primarily through interactions with the dominant winds, and the Coriolis effect, and the fact that, well, water can't blow across a continent like wind can, right? It hits the continent and has to go somewhere. And so that really creates the dominant surface currents. Now, if we're talking about deep ocean currents, well, that's something entirely different. That's going to be driven by density, and density in water, like I said earlier, is primarily a product of the temperature and the salinity. Okay, so why is the sea salty? Well, the sea is salty because rain, right, the hydrological cycle continuously brings water onto the continents. That water interacts with rocks and it dissolves them, right? It chemically breaks them down, or chemically weathers. And so this is a really important term moving forward, chemical weathering. Weathering just refers to the breakdown of rocks. It could be physical, like smashing them into little pieces, or it can be chemical, like dissolving them, right? And so that water dissolves rock, and it transports that material as dissolved constituents, ions, in the water through streams and rivers to the ocean. All right, water evaporates from the ocean continuously and rains, delivering it back to the ocean. Okay, and carrying along with it dissolved material in the form of ions. Okay, so ion is a dissolved species in a solution. Okay, and rivers carry ions to the ocean at a volume of about 4 billion tons per year. It's a non-trivial amount. It's a huge amount of dissolved material that's flowing into the ocean. When water evaporates, it leaves behind dissolved constituents like salts. Okay, and that's why we use distillation as a form of purification, right? Distilled water, like you get from the grocery store to put in your iron, it's collected. Distillation is just evaporating a solution and then condensing it and collecting the condensate, and that's a form of purification because, again, when water evaporates, it leaves behind the salt. Okay, so some of that evaporated water falls back on land and completes the cycle, returning to the ocean with more ions, repeating the cycle. The salinity of the oceans, though, doesn't increase, generally speaking. It's because there are a lot of processes that remove salt from the ocean as well. Things like formation of evaporite minerals, that's just where there's lots and lots of evaporation taking place, so you can form mineral deposits. There are lots of biological processes that remove ions, dissolved constituents from the water. There are also chemical reactions with fresh seafloor that contribute a lot to this process of removing salt. Okay, and so generally speaking, the salinity of the ocean is another steady state, another example of a steady state. The input is generally equal to the output in the system. So the salinity isn't really changing, at least not on short time scales, and really not on long time scales that we can tell as geochemists. Okay, so what salt is there? So salinity is just the total dissolved load in the water. All right, and so what is dissolved in ocean water? Well, it's primarily two elements, chloride and sodium, right? And that's table salt, sodium chloride. It's also a mineral called halite, and so this prefix HALO, halo, refers to salt. All right, so halite is sodium chloride, table salt, sodium chloride. The third most abundant ion in the ocean is sulfate, SO4. It's at a pretty high level, actually, 2.6 grams per kilogram, so that's ppm. No, parts per thousand, ppt. And so, yes, the remaining mineral, or the remaining elements, ions, are in lower concentration. Magnesium's kind of high, calcium is the next highest, and then everything kind of gets lower and lower from there. So primarily it's made up of chlorine and sodium, or chloride is that ion form. Also quite a lot of sulfate. All right. Variations in salinity are caused by regional differences in evaporation, precipitation, sea ice formation, ice melting, and river runoff. Okay, all physical processes. And as it says at the top, except for calcium, these elements are all found in nearly constant proportion to one another. That's a property known as conservative behavior, and it's because it's only really physical processes that uptake or release these. So you can evaporate more seawater and concentrate these things through evaporation, right? But you're going to concentrate them all sort of at the same rate. And so the proportion, they're nearly consistent proportions, right? You can dilute salt water or you can evaporate and concentrate it, but these are all generally found in the same proportion. Now that's different. There are non-conservative elements as well. Those are ones that are involved in biology. As you can imagine, up in the surface ocean where there's lots of light, any nutrients like nitrogen and phosphorus are going to be taken up by biological activity and incorporated into organic material. All right, and that organic material is then distributed through the water column in ways that we'll talk a lot about in subsequent lectures, and it has profound implications on carbon cycling on the planet. But these conservative elements are not involved in biology, and they're generally found in concentrations that look like this. The salinity is here in the middle panel, and salinity is generally lower in the surface ocean, and then it gets higher in the deep ocean, right? But there's this area where the salinity changes rapidly. The same is true of temperature. This is temperature on the left-hand side here, right? We're just going down in depth, 5,000 meters. Temperature in the surface ocean is really high because, as you can imagine, light is penetrating the surface ocean. The upper couple hundred meters of the ocean is penetrated by light, and so it's warmer. It absorbs all that solar radiation, warms up. As you move downward, though, there's this deep, dark part of the ocean that is not warmed by the sun, and so it's colder. And just like in salinity, there's this area of rapid decline in temperature. And these areas of rapid change have special names. In temperature, it's the thermocline. Thermo means temperature, cline means inclined, like something's inclined, it's changing. So thermocline is the area where temperature changes rapidly. Halo, again, refers to salt, and so halocline is where the salinity changes very rapidly. This third panel is just showing density, right? And again, the density of a solution is generally related to the temperature and the salinity. If something has more salt dissolved in it, it's going to be higher density. And if something is colder, it's going to be higher density, all right? And so deep ocean water is very dense compared to surface ocean water, all right? And that helps it stay separate, right? The surface ocean water is lower density, so it floats on top and it's happy to be there, okay? The deep ocean water is denser, and this area of rapid change in density is known as the pycnocline, P-Y-C-N-O, pycno. That pycno refers to density. Okay. And so you have these three areas of rapid change that differentiate the surface ocean from the deep ocean. Okay. And as the text says, the surface ocean is well mixed in exchange with the atmosphere, right? It's driven, circulation is driven by wind-driven mixing. But the deep ocean water is not mixed by the wind. It shows a sharp increase in density related to salinity and temperature. And this stable density stratification just means one thing sitting on top of another, not really mixing. The stable stratification insulates the deep ocean. All right, and the deep ocean accounts for about 80% of the entire ocean volume from changes in seasonal changes in temperature and salinity. All right, there are, however, regional effects. All right, and so this is an example of a regional effect. So one regional effect that we already talked about was coastal upwelling. Right, coastal upwelling is where longshore winds push water offshore, allowing deep water to come up and fill in. So that's an example of upwelling. There's also downwelling, okay, and this is an example of downwelling, bottom water formation. So this is an incredibly important process. It's really what drives deep ocean circulation. So exchange between the surface and the deep ocean, largely driven through bottom water formation. And bottom water is this very dense, deep water that sort of spreads out over the ocean floor. We'll talk more about that in your labs. And really explore it in detail. But at this point, we'll just say that that it forms through, it's created through the formation of sea ice. Okay, and so that's captured here. It forms mostly near the poles, where the surface ocean freezes. All right, and when water freezes, similar to how when water evaporates, it leaves. I could just leave that off, it's fine. Similar to when water evaporates, it leaves the impurities behind. When water freezes, it freezes mostly pure. Mostly as pure water. It excludes most of the impurities. And in this case, we're talking about salt. So most of the salt is left behind when water freezes. So if you freeze the surface ocean, it excludes the salt, and the water that's still fluid, right, that's right below the ice, gets really salty. And so when that water gets saltier and saltier, because water continues to be frozen out of it, the density increases and it starts to sink. It's also really cold, which helps it sink. Okay, and so that sinking water, continuous sinking water from beneath these ice sheets, is what really drives bottom water formation, deep ocean circulation, essentially. And so it says here, as the water freezes, sea ice is formed, but most of the salt is excluded from the ice. The water just beneath the ice becomes saltier and saltier and very, very cold. The combination of high salinity and low temperature results in very dense water that sinks down to the seafloor from where it spreads towards the equator. There are two sites on the Earth where this happens in earnest. It happens around, sort of all around Antarctica, and that's this Antarctic bottom water. And then it happens in the North Atlantic, and that current is known as the North Atlantic deep water current. Okay, and so we have Antarctic bottom water and North Atlantic deep water. All right, and so if we we have this. This is a portrait of the surface ocean circulation. So you have these surface gyres occurring in every ocean basin. All right, that's only in the surface ocean though, and so that surface circulation communicates with the deep ocean really in two places. Deep water forms from surface water in the North Atlantic, that North Atlantic deep water current, and it forms kind of all the way around Antarctica. It sinks down to the bottom, forming this Antarctic bottom water. Okay, and so those are deep currents, but in general, they don't communicate, right? They take those deep water formation sites, take surface water and push it into the deep ocean. Then there are a few places on the Earth where deep water comes up to the surface. It happens a lot in the Indian Ocean and in the North Pacific, and it happens really along the western boundary or the western coastlines of almost every continent. You have strong upwelling. Just like we do here in California, we have strong upwelling. And that returns deep water up to the surface ocean. But surface water, it's really difficult to get surface water to go down there because surface water, like we said back here, right, is generally really warm and not very salty. So you need a process that's going to both lower the temperature and increase the salinity in order to get that water down here and to mix with this dense deep water. All right, and that process is the formation of sea ice. Okay, it's really cold near the poles, and forming ice excludes salt, which means the residual water is real cold and it gets saltier and saltier, and so then it can sink. All right, and so that's how the surface and deep ocean communicate with one another. So you have surface ocean circulation that is driven by the winds, and you have deep ocean circulation driven by density, which is related to saltiness and temperature. All right, and both the atmosphere and the ocean, right, are taking warm stuff from low latitudes and transporting it to high latitudes, right? Water, warm water currents like the Gulf Stream flowing north, taking warm water from the tropics, the Caribbean, up to the pole, right, or to the North Atlantic, and you have atmospheric circulation, warm air rising at the ITCZ and then moving outward. And so both the atmosphere and the ocean are really working to balance, to reconcile this imbalance. Okay, we have an apparent surplus in energy at the equator and a deficit in energy at the poles. Okay, and so because we said, well, the tropics aren't just getting hotter and hotter forever and the poles getting colder and colder, that's not what happens. The Earth works to equalize, and it does so by transporting energy through the ocean and atmosphere toward the pole. And so this graph here is depicting poleward heat transport. Okay, this is northward heat transport in some measurement of watts. And so the total poleward heat transport is there, and about 50% of it is accomplished by the ocean, and about 50% of it is accomplished by the atmosphere. That's sort of the take-home message here, is that poleward heat transport is approximately 50-50 ocean and atmosphere. All right, both of these systems are working together to neutralize that imbalance that we have. Okay, and so if we're trying to establish how the climate operates, well, the climate, that's a big term that captures a lot of stuff, right? But if it has to do with regional weather patterns or areas of high precipitation, low precipitation, hotter areas, colder areas, well, that is really driven by the circulation of the ocean and atmosphere, and how they're taking energy and redistributing it around the planet. Because it comes in unequal from the sun, right? Of course, comes in. We have a higher radiation flux at the equator or in the tropics than we do at the poles. So it's warmer here than it is here. And just like, when you take a metal rod and you put one end in a fire, it's going to get really hot and this end's going to stay cool for a while. But if you take that out of the fire, it's going to tend to equalize. The whole rod will become the same temperature eventually. Systems like to move towards that equilibrium. Hot things don't like to be right next to cold things. They like to transfer the energy. So, all right, so that really summarizes this. The next set of slides is going to be on plate tectonics, which is sort of the next piece of this puzzle, and I will record that later on today, and I'll post it before Wednesday. But this lecture we're going to kind of wrap up today in an hour or two here, and so anybody that's watching these and wasn't in class in the lecture hall last week, you guys are fine. We're not going to take the exam until next Wednesday, I believe, at the earliest, maybe the following Monday, depending upon how fast we get through the material, through plate tectonics. But I will record that lecture later today and have it uploaded for you guys. So thank you very much. I really appreciate you guys working with me. It's kind of an unusual quarter to start on Zoom and then come back and try to figure out how to manage this. But I'm going to try my best to work with you guys and make it possible for you guys to be successful. We want you guys to be successful. We don't want you to get bad grades, and we want you to learn the material. Those are the only two things that matter to us, really. That you guys get good grades and you learn the material. So thanks, guys. I really appreciate it. Bye.